So hello everyone, welcome to this lecture. So today we are discussing about traveling waves in the context of reaction diffusion equations. So more specifically, we are considering the Fischer Kpp equation, which is written right here. Okay. Yeah, this is better. Okay. And with this f of u, so we discussed that a couple of times. And so we look for solutions that write u of xt equals w of x minus ct. So this means that the solution is traveling from left to right at a speed c, at a constant speed c. Okay. So if you replace, you did that a couple of times. If you replace u by w of x minus ct, you obtain equation 2. And with this transformation, you obtain these ordinary differential equations of order 1. Okay. And so we started to look into this solution, this equation, and we found that there was 2 stationary points, 0, 0 and 1, 0, 0, and furthermore, computing the Jacobian matrix, we had the following proposition, meaning that when C is negative, 0, 0 is a source. Oh, there's a typo here, but if C is positive, maybe we will, let's correct that right now. So if C is positive, right? So if C is positive, it's a sink, right? And so for C greater than 2, the 2 eigenvalues of the Jacobian are real. So it was a node, in this case, a stable node if C is positive, and an unstable node if C is negative. And if C is between -2 and 2, 0, 0 is a focus, right? So a stable focus if C is between 0 and 2, and an unstable focus if C belongs to -2, 0. And for the other stationary point, 1, 0, it's a saddle node because we have 2 eigenvalues of opposite sign. All right. So you did those computations, and that's what we found. All right. Okay. So furthermore, we did some computations, and here are 2 typical cases of positive C. For C equals 1, so we have a focus. And for example, in purple, you have let me put that in purple. You have a trajectory here. In green, it's the null line for P. Okay. And so the other null line for W, so W prime is positive if P is greater than 0, and it's negative if P is negative. So, and in purple, you have a solution. Then when you cross the null line here, the derivative of with respect to P becomes positive, and you start to increase. And here you can observe that the dynamic is coherent with the focused nature of 0, 0 for C equals 1, right? We did more last time. We illustrate other solutions for C even smaller, and so the trajectories were rotating more. Okay, and then we have the other case, which is a typical case of C greater than 2, and here 0, 0 is now a stable node. And so as you can see, so just to remark here, it's like a slow fast system because the trajectory follows quite closely the null line. But so you have a solution here. So in green again, you have the null line for C equals 4. Here the value of P are very small, and when you cross this null line, so the solution, the orbit decreases with respect to P, and then you cross it again, and it increases, and it goes to 0, 0. It's attracted by the stationary point 0, 0. Okay, so now what we want to do. So that's what we did last time, all right? So what we are going to do today, oh, again, there's a typo. Let me correct that again, because I don't want this to stay. I don't look for a homoclinic orbit. An homoclinic, it's a trajectory which goes from a stationary point and comes back to it. But we look not for a homoclinic orbit, but for an heteroclinic orbit. All right. And so here I represented the same trajectory, right? This is one trajectory which corresponds to one initial condition. What I'm looking for, what we are looking for, is for a solution that is defined for all times for W and P, but which starts or which goes to 1, 0. So 1, 0, let me point to the 1, 0 stationary point. The 1, 0 is here. I would like to prove the existence of the trajectory which comes from 1, 0 and goes to 0, 0. So here the solution goes to 0, 0, but she's going somewhere for t is when t goes to minus infinity or so. Okay. So how can I do that? Does somebody have an idea? So first, is there some tool that guarantees, that ensure that a solution is coming from the stationary point 1, 0? Do I have a tool which guarantees that? Does somebody have an idea? I'm listening to you. Okay, we will come back to that later. Now, oh, I see something in the chat. Yeah, but that's not enough. The sign, it's not enough. Okay, assume that I have a trajectory. Let's just assume that I have a trajectory which starts here with the blue. Actually, what's the blue? What's here? What's this line here? Does somebody have an idea? What can this blue line represent? Yeah, but it's not enough precise. Okay, so let's just assume that I can find a trajectory that starts from 0, 0. So I have no choice. If a solution starts from 0, 0, it is stuck in this side because here, so here the derivative with respect to W is negative here, so I will enter here this line, so I have no choice. So the solution, it's like the red one. It has to be there, and so it decreases. So if a solution starts from 0, 0, it has to follow somehow this red line, and eventually it will cross this null line. It has no choice. Okay, if you look at the signs, maybe we can go with some detail here. If we go with the signs here, so here, let's change the color. Here, the derivative of P is negative, right? So if I have a solution who starts from 0, 0, it has to decrease. But it cannot cross this green line because the derivative here with respect to P is positive. So I'm stuck here in this region, but what I can do, I can cross it somewhere, so then the trajectory can cross somewhere here. For example, the red one, you see that at some point she's crossing this null line, and then of course here in this part the derivative with respect to P is positive. All right, so it will increase. Okay, so this red curve is going to 0, 0, but we cannot say that from the geometry, because the question is it possible that, so let me draw another curve. So this part here is typical, but now why can I have a solution who is going like that and crossing here W equals 0? Is that possible? So here I respect the fact that P prime is greater than 0 in this region. Again, P prime is greater than 0, and it could it could cross this line. But in fact, what we are going to prove is that, in fact, there is a line which I represented here with a yellow line, that a solution that starts from 1, 0 cannot cross, which means that at this point, any solution that comes here, so the solution have no choice. He has to do something like that. This comes from the nuclides. And what we need to prove is that this cannot happen. This impossible. All right. So we are going to prove that there's a line, a yellow line, such that the trajectory will remain stuck in between the yellow line and the green line. So it has no choice. It has to go towards 0, 0. So if you prove that, we have a heterochronic orbit, because also I have a theorem that ensures that some trajectory exits 1, 0 like this. Okay? Any questions so far? So now, what's the tool that ensures that it exists a trajectory? So there is a question on chat. I'm answering to that. Why heterochronic? Because we are going to prove that there's a trajectory that starts from 1, 0, which is a fixed point, and goes to 0, 0, which is another fixed point. So hetero is for different. So Greek stuff. It's a Greek heritage. Okay, so heterochronic, it's because there are two different stationary points, and the trajectory, we are going to prove that some trajectory connects these two different stationary points. 1, 0 here and 0, 0 here. My two stationary points. All right. Okay. And so I have a theorem that ensures that a trajectory is ensured from the stationary point 1, 0. All right. This is because I have a stable saddle node. I have a saddle node, and okay, we computed for example, C equals 4. We computed the eigenvectors associated with the stationary point, and I know that there is some trajectory which is tangent to the repulsive eigenspace associated with the eigenvector associated with the positive eigenvalue. All right. And so I have the term. So I picked up from another course. So the references, some numbers may not be accurate, but we will comment that. So, okay, this is my theorem. So in fact, here in blue, what I represent here, it is the eigenvector associated with my eigenvalue, which is positive for the Jacobian. And if you look here, you see that I'm reading with you. There exists a differentiable manifold, I call it I, but with dimension n minus 4. So here it's 1 because I have a a saddle node. I have one positive eigenvalue and one negative eigenvalue. So here it's a line which is tangent to the subspace. So here it's the eigenvector of the Jacobian. And so it says what? It says that when t goes to minus infinity, the trajectory here goes to the point 1, 0, because here my 0 is it represents the stationary point. So this provides the existence of a trajectory that comes out of 1, 0, right? So here I have the stationary point 1, 0, and I do have a trajectory which comes from here, right? Okay, so now it starts from there. And so it has no choice. It goes like that. It decreases, and at some point, it crosses the green curve, which is my neckline. So the derivative becomes positive, and so sorry, and so let's. It's not right, but something like that, right? It's not right at all. And after, it will be stuck between this yellow line and this green line. Okay. All right. So one part is okay. One part is okay. So the yellow one. I'm just telling you, we didn't prove nothing about the yellow one. I'm just telling we are going to prove that. And no, it cannot touch the yellow line, but we have to prove that. The other things, if you think about it, you have all the tools. You apply this theorem, and then from the null lines, you can deduce that the trajectory has no choice. It has to cross the green line, and then P increases, and then I'm stuck between the green and the yellow, so I have to go to 0, 0. Okay. So the omega limit set and the alpha limit set is related to that. It's related to that. You have to think more about it. It's not exactly the same. So you can define first the omega limit set, for example, for a point, and then the omega limit set of a set. Yeah. All right. So you have to think about that. Of course, these things are very related with what we are doing right now. Yeah, so we have to prove it. We have to prove that my trajectory will not cross the yellow line. So that's the point. That's the point of what we are going to do today and right now. Okay, theorem. For c greater than 2, there exists a heterochronic orbit. So Wt, P of t for t belonging to R, which connects the point 1, 0 at t equals minus infinity and 0, 0 at t equals plus infinity. Yeah, so with respect to the question of Mr. Hamatouche, that's what we are going to prove. This can not happen. The trajectory cannot cross x equals 0. And so it has no choice. It has to go towards 0, 0. So, yeah, let's go to that. And in order to prove that, we need, so again, the numbers here are not correct because I picked that up from another notes. But so I'm interested here in recalling the definition of an upper solution. So when you have an ODE, let's assume that our ODE is U equals F of TU. So an upper solution is when you replace the equal by greater. Okay. Here, what I do, the definition of an upper solution is like the solution of the ODE, but I replace it with a sign greater than. Okay. So if you have that, and if the initial condition for my U plus is greater than the solution, the initial condition for the real solution of the ODE with the equal, then the upper solution will remain greater than the solution. Okay. And now what we have is we are going to prove that my yellow line represents what? Represents an upper solution of an ODE which gives the trajectories. Okay? So upper solution, you replace the equal in the ODE by greater than. Okay? And you have also to ensure that this is true for the initial conditions where you start. Okay? Okay, then so we are considering this equation. What does it come from? So I ask you to write it. So please write it. I'm stopping here. Write GP divided by dt. Okay? So now if I look at the equation GP divided by dW, which is the fractions of GP divided by dt divided by dW divided by dt, I got that. And so now we are going to prove that the function that I define as P of W equals minus W. So this one, I define it. It's not a solution of any ODE. It's just a function of W. And it satisfies at 0, P of 0 equals 0. So I'm going to prove that this function, which which is very regular. I can derive it with respect to W, and its derivative it's -1. And I'm going to prove that for W in 0, 1, for W belonging to the interval 0, 1, I have that the derivative of P is greater than the right-hand side of equation 4. All right. Okay, so if I take the derivative of P, it's -1. So I just put -1 plus 1 and minus W. Since I'm considering positive W, this part here is greater than this part here. But now, since my P, so just now I can put -W here and here. Okay, I regroup -1, it's -2. And here, now I recognize my F of W. -W is P, and 2 is less than C, so -2 is greater than -C. So I got that P, defined as P of W equals -W, is an upper solution of equation 4 of the ODE 4. All right, and that's it. So now this means what? If I come back to my picture, is that you have a solution which starts from 1, 0. It has no choice. It has to come like that. Then it crosses. It has no choice. It has to cross the null line in green. And then in yellow, it was my function P of W equals -W. And you have no choice. This red curve cannot cross the yellow one, because if it crossed, and then if it didn't go to 0, then it will cross the axis, the W axis, and this will contradict that P of W equals -W is an upper solution. Okay, so that's it. We proved. This proves that we have a heterochronic orbit from 1, 0 to 0, 0, and this corresponds to a traveling wave for my reaction diffusion equation. All right. So we need to prove this theorem. We're going to prove the theorem. Just some references. So the results about dynamical systems of ODEs, you can find that in these two books. And this is a book on traveling waves. It's yeah. And then the two papers of Fischer and Kolmogorov, Petrovsky and Piskunov. You have a lot more references, but that's a good start. Okay, so what we are going to prove now is that we are going to prove the result on the upper solution. Okay, so we are going to do that right now. So what we are going to do now is to prove this proposition on the upper solution. So we assume that we have two functions that are well defined and regular. And so we assume first that, for example, we have a function u1 which satisfies an ordinary differential equation. So we assume that everything is regular. And on the other side, on the other hand, we have that u2 prime satisfies not the equality, but an inequality with a greater. So u2 prime is greater than u2, f of u2t. Okay, and we assume that at time 0, we have u2 0, which is greater than or equal than u1 0. So then we want to prove that we want to prove that then u2 of t remains greater than u1 of t. So u2 of t, sorry, is greater than u1 of t for all t greater than 0. We assume that everything is well defined on the real line. Okay, and so assume that it is not true. So if it's not true, so assume that there exists s greater than 0 such that the equality holds, meaning that u2 of s equals u1 of s. All right. Now let's write the derivative for any t, u2 of t minus u1 of t. I take the derivative, and this is u2 prime of t minus u1 prime of t. And with our assumptions, I know that this is greater than f of u2 times t minus f of u1 times t. So for t equals s, we obtain that u2 minus u1 prime I times s greater than 0, because we assume that for t equals s, u2 of s equals u1 of s. And so we assume that s is the first time. It's the first time that we reach the equality. So before, we would have, if you look at the assumptions in detail, we will have that u2 of t is greater than u1. So before, meaning that for t less than s, so we assume that s is the first time that we reach the equality, we have u2 U2 of G is greater than U1 of G. So if you have that, then this implies that U2 minus U1 prime of S is less than 0, because if you look at the difference, since U2 is greater than U1 for T less than S, this implies this thing. So we got a contradiction, right? We got a contradiction because here we have this, and here you have this. And so that's not possible. So this S doesn't exist, right? And that's it. And so with that, see you next week or next time.